Okay, so nodal basis. Well, let me say first of all, this is not actually an accurate representation of what we had over here, because we also need to enforce the boundary conditions, right? So basically, we need we want a nodal basis for the kind of functions that are 0 here. It can be any value within and go back to 0 over here, right? So this is the kind of a function we want to construct the basis for. So it can also be like this, right? It can be like this, right? It can be anything you want, right? Okay, so these are the kind of functions we want to construct a basis for. So the key thing to think about is, what if A1 is equal to 1, A2 equal to 0, etc., A n equal to 0. So if only one of these coefficients are equal to 1, the others are equal to 0, then what is f? F is equal to, remember, the combination of the basis with the coefficients. So if A1 is equal to 1 and all the others equal to 0, then this is just equal to W1, right? Okay, then we should actually be able to construct what W's are just by setting these coefficients. Okay, so for example, if A1 is equal to 1, and remember, set that nodal basis means that AI is actually equal to the function at xi, at one of these grid points, at one of these nodes, right? AI is the ith node, xi is the ith node. Okay, then what is it? So if the value of the function is equal to 1 at the first node, so let me actually draw it over here. So if n equal to 0 at all the other nodes, what is the function? It's just a function going up and down and 0, right? So that's going to be my W1. Okay, so again, let me set A1 equal to 0, A2 equal to 1, and A3 equal to etc. equal to 0. Then my F is the linear combination AI Wi is equal to W2, right? So that by that way I figure out what is W2. So basically I set A1 to be 0, A2 to be 1, and A3, A4, etc. to be 0. So my function is this. All right. So that's my A2. That's my W2. And W3 would be setting this to 0 and this to 1. So this is my W3, and my W4 would be, well, I think I set too many different colors. My W4 would be, let's use maybe this. This is going to be my W4. All right. How do I get back to the colors I used before? Oh, okay, good. All right, so this is my nodal basis. Basically, each W is just what we call a hat function, right? So it's basically 0 and like a sharp hat to one of these nodal points. Okay. All right. Let's see. So this is an example of how do you construct a basis. And next, what we want to talk about is, now we have the basis, how do we solve the equations? Okay, so basically, all a finite element method is doing is to convert a problem that is the weak form. So weak form, which is A of V W. Let's use plus equal to 0 for all v within X, and such that the constraint is W is in a, let's right, so let's make this X0, because they actually can be in different spaces, right? So for example, remember our discussion of the inhomogeneous boundary condition. So if not here, if my W0 and W1 are WL and WR, then V and W has to satisfy different boundary conditions. So the space they are in has to be different, right? Slightly different usually, just to differ in the boundary conditions. But that is sufficient to make this X0 and X to be potentially different. All right. So we are basically going to convert that weak form into the finite dimensional. So basically, we are going to be writing the weak form exactly as it is, but we are going to say V has to be in a finite dimensional X0, such that also W has to be in the finite dimensional counterpart. So finite element is basically converting the weak form, restricting the weak form in a finite dimensional space, and that's it. All right. And let's see how does the basis going to then turn this into, well, so this is we use the basis to turn this into AX equal plus B equal to 0. Okay, so that's the help of the basis. Well, the basis does two things to help with this. One thing is that it represents V. It can represent any V as a linear combination. All right. So the notion of any V within X0 is basically saying that any A1, A2, etc., AN that makes V equal to summation of AI WI, right? Okay, such that W is within X is also simply saying that for such that W is actually a linear combination of, let me just say, Xi times Wi. Does it make sense? Right. So basically, the solution, instead of being an unknown function within a space, it becomes these linear combination coefficients, right? So we are no longer solving the weak form for some function W. We are now solving the weak form for a set of unknown numbers x1 to xn. Also, we no longer have an equation that has to be satisfied for any function V. We now have a set of equations that has to be satisfied for any choice of a finite set of numbers. All right, and also the linearity of the weak form with respect to V actually helps a lot. So look at the whole first equation. If I fix W, the first equation is completely linear with respect to V, right? And that means if this equation is satisfied, for example, for W1, it's also satisfied for W2. It is satisfied for actually any linear combination of W1 and W2, right? So if V is equal to W1 satisfies, V equal to W2 satisfies, then any combination of W1 and W2 also satisfies. So in particular, if I just have to enforce the first equation for V equal to each Wi, I actually enforced this equation for actually any V being any linear combination of these Wi's, which means I have enforced this equation for any V in X0. Make sense? Okay, any questions on this?